Morning, everyone. How are we doing? Let's start with Tony's question. I'm sure you tried a few paths, right? Namely, if x is 0 in the yz plane, so you try a few paths. And when x is 0, this is 0 over y squared plus z squared, which is 0. So if the limit exists, it has to be 0. You can try on the xz plane and on the yz plane, on the xy plane, and you can try a few paths. You always get 0. That's my claim. I'm sure Tony tried it already, and you were always getting 0. So now we have to prove it. Right? For those of you who haven't seen this question before, you should try a few other paths. Make sure that 0 is what you get. It's not immediately clear. I don't want to waste too much time, but you will get 0. So now we got to prove it. So I'll claim let's prove it. And let's write down what needs to be proven. We have to show that for epsilon greater than 0 given, there exists a delta greater than 0 such that if this is close to 0, then your function minus 0 is less than epsilon. This is what needs to be proven. So let's start with exactly that. Let's work with that, see what's happening. Well, first of all, let me point out that this thing, what is that? xyz minus 0, 0, 0 is just xyz. And the norm of xyz, you know, to be the square root of x squared plus y squared plus z squared. So it's this that's less than delta. So if we start with that, which is really just, everything's positive here, and the minus 0 is not doing anything. And let me make this bigger by throwing in, instead of just x squared, let me throw in a y squared. Right, I'm throwing in this extra positive term, I'm making everything bigger. And you know, I mean, I'm doing it in 2 steps, but let me throw in yet a third, well, yet a second term, a z squared, which is positive again. And now you see that these 2 things cancel out nicely. And what? So now we're left with y squared z squared, which is, by the same idea, this y squared is less than x squared plus y squared plus z squared. And this z squared is less than x squared plus y squared plus z squared. So we get x squared plus y squared plus z squared all squared. So now you see what's going to happen. This, well, the square root of that is less than delta. But we have this thing to the power 4. So we're going to take delta to be epsilon to the 1/4. Right? This is really the square root of x squared plus y squared plus z squared to the power 4. So that is less than epsilon to the 1/4, the whole thing to the 4, making it less than epsilon, exactly what you wanted to prove. Prin is asking if the limit was not 0, if the limit was 1/2, you would have to put everything over a common denominator here. Absolutely. Don't bring a plus or minus L into the epsilon. Everything would be the same. You wouldn't want epsilon to depend on L though. So I mean, the only place it would change is right here. Put everything over a common denominator and then work from there. Yining was asking what is the minimal degree Taylor polynomial about x equal to 0 that you need to calculate cosine 1 to 3 decimal places. Well, let me ask you this. What did you do? You worked that out, I suspect. Tell us what you did. Vin is also asking if we can draw x squared plus 2y minus 2z squared is equal to 0. Let's do that. Yishen is asking if we can substitute the denominator with delta. Let's not do that, right? Because here x squared plus y squared plus z squared is going to be less than delta squared. And when you cross multiply, the inequality is going the wrong way. So you do not want to do that. Quinn is asking for us to sketch this. Let's sketch. Let's sketch by bringing the z to the other side. So we get 2z squared is equal to x squared plus 2y, or z squared is equal to 1/2 x squared plus 2y. Well, I guess I could multiply it in. Or z is plus or minus the square root of 1/2 x squared plus y. So let's just concentrate on the positive square root first. And of course, there's going to be symmetry about the xy plane. The same thing is going to happen on the bottom. Let's graph that. So let's look at just the positive part. And again, we're going to graph this in the xz plane. If y is 0, we get z is 1 over root 2 absolute value of x. So you know what that looks like. Just a straight line, those two, that V shape. And if x is 0, then you have z is the square root of y, which is only possible if y is positive. So, yeah. And now let's put this together. How do we put all of this together? When z is c, the level curves, what do we have? We have z is c, so x squared plus 2y is equal to 2c squared, or y is equal to 2c squared minus x squared. So these are parabolas coming down. So everything is put together with parabolas coming down in the y direction. Like this. So what does that look like? Can we give an idea? Kind of cone-shaped, like this, but instead of having a straight line like that, it's actually curving out like the square root of x. So I can't kink this, but you understand the idea, right? I mean, this is gonna follow that, but it's going to open up in that direction. So like this, yeah. Why was it epsilon to the 1/4 to the 4 rather than less than or equal to? We had assumed square root of x squared plus y squared plus z squared was less than delta. It was a strict inequality. Fiona is asking how we're going to get the midterm and go about handing it in. Everything's going to be done through CrowdMark. I still haven't had time to actually write the midterm or set anything up because I'm still doing the 141 business. Hopefully I'll get to that today. And you will receive an email from CrowdMark if you've never used it. You'll receive an email from CrowdMark. You'll have access to the midterm starting Friday, 2 p.m. And you'll have 72 hours to upload your answers to CrowdMark. Do not wait for the last moment. If your answers are not up within 72 hours, you will get 0 for the midterm. We consider C a constant. Absolutely. It is the level curve. So it's a function between x and y. Exactly that. The level curves bring everything down one dimension, and we now have just a curve in the xy plane. Although it is at some height z, it's really just a two-dimensional object. Well, really a one-dimensional, but it lives 2D. Yeah, Brun is suggesting sometimes plugging in 0 doesn't work. And I mean, you're right. Sometimes 0 is not in the domain. So, you know, we have to adjust. I mean, there's no one way. This is something that works nicely, but there it is. Ran is asking, do we always find the relationship in terms of x and y? Sometimes you cannot. Sometimes it's better to find it in x and z. Again, you have to adjust. Will it become a string after some distance? I'm not sure what that question refers to. Mantha? The Amar, my email is still working. There shouldn't be an issue. Maybe there was a momentary issue, but I am getting emails. Try it again. What about the negative? Right. Yeah. What about negative z? Thank you. I was going to forget that. It's plus or minus the square root, right? So here we just drew the positive square root. The negative square root is going to be the same thing, right? Just no. Just a mirror image, right? So you're going to have the It's really a mirror image about the xy plane. So it's a reflection about the xy plane, right? Because whatever happens on top happens on the bottom as well. So Fiona's asking for the midterm, you handwrite it and you scan it. I will accept pictures as well. It doesn't have to be a scan. Good quality pictures using an iPhone or a tablet, whatever. The cameras are very good. So let's say this. Take a picture, upload it. If you can read it, then the marker can read it, and it's all good. Can you use X to determine the shape? I'm not sure what that means. I mean, we're making use of the function in X and Y, but there it is. Questions here? So last time we introduced, we were talking about limits. Yeah, the email Pun is suggesting will work as well. Yeah, I mean, both emails go to the same thing. So Mia's asking, what textbook chapters will the midterm cover? Certainly everything we've done so far. We'll see how far we get today, and we'll discuss that after class. Yeah. So last time we were talking about limits, and as you know, in Cal 1 we use limits to define the derivative. We're going to do the same thing here. Definition. Given a function of two variables, so given a function f of xy, Avery is asking if this is all in the 141 textbook. It is not. It is not unless you bought the big textbook, which does cover it, so it depends. The textbook we were using for 141 really stops at chapter 11, sequences and series. This is, I want to say, chapter 13. So depending on if you bought the complete course, you might have it. Otherwise not. Yeah. But if you don't want to buy a book, or it's probably difficult to buy a book in these trying times, I have given you a list of online resources that you can use. Our book is not there, but there are excellent books there anyways, and the important thing is to do lots of exercises. So whether you're doing exercises from Stewart or from Adams or any other calculus textbook, it really doesn't matter. Given a function of two variables, f of xy, we define the partial derivative of f with respect to x. Denoted df dx or fx of xy or dx of f of xy, or f1 of xy, the derivative with respect to the first variable, as, right, so all of these are just notation for exactly the same thing, as the limit as h goes to 0 of f of x plus h, y, minus f of xy over h. Tony is asking if we're going to learn polar coordinates. We will. We will learn polar coordinates. Satya is asking if we can use engineering mathematics. I'm sure if it covers the material, then you're good to go. Right now, what are we doing? We're doing partial derivatives, right? We are defining the partial derivative. Any book that introduces partial derivatives can be used to learn the material. Lots of exercises is what you want to do. So we're giving here the definition of the partial derivative with respect to x. Similarly, well, first let me bring your attention to the fact, what is this? Here we are measuring we're measuring the change of f as the x variable changes. So it's really a generalization of the regular derivative here applied only to the x variable. We can do the same the partial derivative of f with respect to y denoted df dy, and notice these are squiggly d's to as opposed to the straight d's, right, to distinguish between the regular derivative and the partial derivative. So df dy or fy or dy or the derivative with respect to the second variable. This is the limit as k goes to 0 of f of x y plus k minus f of xy over k. Of course, here k is just a dummy variable. It might as well have been h, but it's customary to use k. Not sure why. Tony's asking, what does f1 mean? Exactly. f1 is this, and it's also that, and it's also that. It's notation for the same thing. Namely, the partial derivative of f with respect to x. 1 here meaning the first variable. 2 meaning the second variable. And if you take a step back, what's happening? Here only the x's are changing. We're not touching the y's. Here only the y's are changing. We're not touching the x. Kun is asking, can we differentiate with respect to both variables at the same time? There's something you kind of can do. It's called the total derivative. The book discusses it. I was not going to discuss it at all. But yeah. Something can be done called the total derivative. But what it actually is just essentially the sum of the two partial derivatives, if you will. Does this mean we cannot change the order of the function? I don't know what that means. Given that f1 and f2 need to be constant, still I'm not sure what you mean by that. Let's take a few examples. Maybe this will clear things up. And let me take an example, an easy example to illustrate what happens. We cannot write x plus y as y plus x. You can do that. It's not an issue. It really is not an issue. So if the limit exists, applies for both, these derivatives work. Of course, it's under the assumption that the limits actually exist. Yes. I should have said that. Right? The partial derivative is equal to this limit under the assumption that the limit exists. If the limit does not exist, the partial derivative does not exist. Let's illustrate with this simple example, and you'll understand exactly what happens here. df dx, which is the limit as h goes to 0 of f of x plus h minus f of x plus hy minus f of xy over h. What is that? Everywhere you see an x, you replace with x plus h. So we get x plus h squared root y minus x squared root y over h. And notice that you can factor out a root y which does not depend on h. Leaving you with x plus h squared minus x squared over h. And if you take a step back, you will recognize this limit to be just the derivative of x squared. So in this partial derivative of f with respect to x, what has happened? Anything that depends on y is left aside, and you just differentiate with respect to x the stuff in x. So this is root y times the derivative of x squared, which is 2x. So the part of the function that depends on y is treated as a constant because there are no x's there. And there it is. And you just differentiate the parts that depend on x. Let's repeat with the derivative with respect to y. By definition, this is the limit of f of x, y plus k, minus f of xy over k. So what do we get here? This is x squared, square root of y plus k, minus x squared root y over k. And again, if you factor out the x squared, you get this. And again, you recognize this, well, the limit of that, to be the derivative of the square root y function, leaving the stuff in x fixed. So this is x squared times the derivative of square root of y, which is 1 over 2 square root of y. And this idea extends to all functions. When you have a function of x and y, the derivative of f with respect to x, you treat the y's as constant. And you just differentiate your function with respect to x. Similarly, if you're differentiating your function with respect to y, you treat all the x's as constant. And as Brun suggests, this extends to higher dimensions as well. If you've got a function of x, y, and z, we can ask for the derivative with respect to x, with respect to y, with respect to z. And in that case, when you're differentiating with respect to one of the variables, you treat all other variables as constant. Let's illustrate with a few examples. Avery is asking, if k is approaching 0, how does that become the limit? Exactly. Somebody want to address that? First of all, this x squared does not depend on k, so you could take that outside. So really the question is, how do you evaluate this limit? Well, first of all, without actually working it out, let me write an x squared here. My suggestion to you is convince yourselves that this is the definition of the derivative of the square root of y, right? If you had g of y equals root y, this would be the derivative g prime. And you know the derivative is 1 over 2 root y. But, as Amar suggests, you could evaluate this limit directly by multiplying by 1, namely root of y plus k plus root y over itself, the conjugate, and you get y plus k minus y over k square root of y plus k plus root y. The y's cancel, and then the k's cancel, leaving you with a limit of 1 over 2 root y, exactly as expected. Cecilia is asking, is the partial derivative the rate of change of the function with respect to one variable? Exactly. Let me illustrate graphically what is going on here. Let's illustrate what's happening with a partial derivative. you have this function hovering above the xy plane, and if you fix a point, look at the image, right? So fix a point AB, look at the image, this is f of AB, and what are we looking for? We're looking for the rate of change in the x direction. So if you were to slice this function at that point parallel to the x-axis, right? Imagine cutting it. This would map out some curve. And what we're looking for is the derivative at this point of that curve. That is, so this tangent line here, that is fx. The slope of the tangent line is fx. Similarly, if you were to cut it in the y direction, this would map out some curve, right, in the cut there, and we're, again, fy is the slope of the tangent line, fy at AB would be this slope right here. So that answers Tony's question as well. Does the partial derivative represent some kind of slope? It absolutely does. So the limit is not a number, but rather a function. Well, I mean, in general, right? I mean, here you get a rule, if you will, that gives you the slope at each point. In very much the same way that the derivative of x squared is 2x, here it's a function, so here it's a function as well. Evan is asking if the plane defined by those two vectors would be the total derivative. Not quite, but the plane defined by these two vectors is going to be important momentarily. So a very nice question there. Not quite the total derivative, but an important concept nonetheless. And this concept of cuts, of course, extends to higher dimensions. So that's what the partial derivatives would be in higher dimensions. Say a few examples from the book. We are asked to find the partial derivatives . Of course, you're welcome to set that up using limits, but you know that in Cal 1 we didn't spend any serious amount of time doing that, and of course we're not going to do that here either. We've understood that in the limit process, when you're differentiating with respect to x, all other variables are kept constant. When you're differentiating with respect to y, all other variables are kept constant. So we're going to jump right into that and say df dx. And of course, all the rules of differentiation extend immediately. Product rule, quotient rule, chain rule. The derivative of a sum is the sum of the derivatives. and so on and so on. So here, if we're looking at the first part, this is x squared times y. We're differentiating with respect to x. So y is kept constant. The derivative of x squared you know to be 2x. So the derivative with respect to x of this part is 2xy. Derivative with respect to x of this, there is no x. Y is treated as constant, so the derivative is, you know what it is. Zero, thank you. Absolutely. Oops, I'm jumping the gun here. So this is the derivative with respect to x. Marathon, I think you're answering maybe the next question. What about the derivative with respect to y? Right, so here in this first part, x squared is treated as a constant. The derivative with respect to y of y is just 1. So we get x squared times 1. And then the derivative of this with respect to y is just 12x cubed. There it is. Absolutely. Consider this. A function of x and t, don't let the t fool you. Whether it's t or it's y or it's z, it's all the same. Here we ask the question, what is the derivative of x with respect to t? Well, I mean with respect to x. So we're treating t as a constant. Here you've got an exponential. So the derivative is e to the xt times the derivative of the inside. T is a constant, derivative of x is 1. There it is. Similarly, the derivative of g with respect to t, again an exponential, e to the xt, times the derivative of the inside. This is constant, derivative of t is 1. Amar is asking if there's any link to implicit differentiation in these questions. There's a very, very nice link. Absolutely. Absolutely. We're going to see that next week. In fact, we're going to give an extension, if you will, of the implicit function theorem. We're going to give a nice generalization of the implicit function theorem, and we're going to see that the results we had for implicit differentiation in one variable, or in the 140 case, are actually a simple consequence of the implicit function theorem in several variables. Again, we're looking for the derivative with respect to x and with respect to y. You know what to do. You've got something cubed. So we're going to differentiate the cube first. And then you differentiate the inside with respect to x. Derivative of x squared is 2x. Here the y is treated as a constant. Derivative of x is 1. And there it is. Similarly, if you differentiate with respect to y, again it's something cubed. So differentiate the cube first, and then you differentiate the inside. Derivative of x squared, you tell me. Derivative of x squared with respect to y is 0. Absolutely. Thank you, Rebecca. So 0, let me write it for completeness. Derivative of x squared is 0. Derivative of xy, x is treated as constant. Derivative of y is 1. So there it is. Is everybody with us here? How are we doing? Let's do a few more. Let's differentiate with respect to the first variable. You recognize you've got x here and there. This is a quotient. So quotient rule applies. V u prime minus u v prime, the derivative of this, it's something squared, so 2x plus y times the derivative of the inside. Derivative of x is 1. Derivative of y is 0. All over v squared. Let's cancel one of these, leaving you with x plus y minus 2x over x plus y cubed, or x minus y if you prefer. There you go. Similarly, if we ask the question, what is the derivative with respect to the second variable? I'll give you a moment to work that out. But it's easily seen to be this, right? You don't have to use the quotient rule here. The only place you've got a y is here. So this is really x times x plus y to the negative 2. Differentiate, blah, blah, blah. Negative 2x, x plus y to the negative 3. Everybody with us? A nice question. Take a moment, work out the first partial derivatives. Does everybody have it? What is it? This is x to the power y. The derivative is yx to the y minus 1. Very nice, Tony. What about df dy? This is x to the y. The derivative is, very nice, x to the y log x. Exactly that. Right? When you're differentiating with respect to x, this is like an x cubed. So you bring the power down and you subtract 1 from the power. But when you're differentiating with respect to y, this is like a 2 to the y. So 2 to the y ln 2. df d alpha, you know exactly what that is. Right? And df d beta. How's everybody doing here? Questions? Let's do one more with a function of 3 variables now. Quinn is asking if we can partially integrate as well, right? I mean, that would make sense. And that's exactly what double and triple integrals are all about. We're going to see that not next week, probably the week after. Or maybe towards the end of the week, next week. Ryan is asking, why is alpha negative? You tell me. Somebody want to address that? Right, you know by the fundamental theorem of calculus, if f of x is the integral from a to x of f of t dt, the derivative is little f of x. The variable has to be on top though. Here alpha is on the bottom. You know what you're going to do. You're going to switch the limits by taking a negative. This is negative of the integral from beta to alpha. And now you're in a position to use the fundamental theorem of calculus. Consider now a function of 3 variables. You've got a function of 3 variables. So we can ask the question, what is the derivative with respect to x? What is the derivative with respect to y? What is the derivative with respect to z? Let's work these out. Here, when you're differentiating with respect to x, you're going to treat y and z as constants. So you have this times that. You've got a product, so product rule applies. Derivative of x, y squared is just y squared. Plus, you leave the xy squared fixed, and you differentiate the exponential. The derivative of the exponential is the exponential, times the derivative of the inside with respect to x. Z is treated as constant, the derivative of x is x, so you get negative z. Derivative with respect to y, x and z are treated as constant. So the only thing that depends on y is this, and we get 2xy e to the minus xz. Finally, the derivative with respect to z, x and y are treated as constant. The only thing that depends on z is this. It's an exponential, so the derivative is the exponential times the derivative of the inside. Derivative of z is 1. You're left with this constant, negative x. How are we doing? Somebody was talking about, Amar actually was talking about implicit differentiation. Why don't we take an easy example of that idea? Suppose you had an equation. Yes, Quinn is asking, the product rule only applies to the x variable because it's present more than once. That's right. Here, this is a function of x, and so is this. So it's a product rule there. Exactly. In the other cases, the variables are treated as constants. So you only have y here, and you only have z here. So exactly that. So consider this equation here, where you've got one equation involving x, y, and z. Theoretically, you could isolate for one variable in terms of the other two. Theoretically, you might be able to solve for z as a function of x and y. Let's not do it, but you understand that, at least in theory, it may be possible. Now we're going to ask the question, if this is the case, what is dz dx and what is dz dy? So I guess what are dz dx and dz dy? Nice of you to join us, Wayne. Welcome. Right, so what is dz dx? What is dz dy? That's the question we wish to answer. What are we going to do? We're going to differentiate the whole equation with respect to x, with the understanding that z is really a function of x and y, even though we never actually solved for it. So differentiate the whole equation. The derivative of x squared is 2x. We're differentiating with respect to x. The derivative of y is treated as a constant. So this is going to be a constant. The derivative is 0. The derivative of z squared, well, z is a function of both x and y. So, first of all, you've got something squared here, so you differentiate the square, 2z, and then you differentiate the inside. You differentiate z, but z is a function of x and y, so you get dz dx. Because you don't know what z actually is. We never really solved for it. But whatever it is, you would then differentiate z with respect to x. Well, Bluebill is asking, isn't y also a function of x and z? Well, that's the thing, right? I mean, it depends what your initial assumption is. You have one equation, 3 unknowns. So you could solve for one in terms of the other two. Here I'm suggesting we're going to solve for z as a function of x and y. If we do that, it's understood that x and y are the independent variables and that z depends on both x and y. You could have solved for y as a function of x and z. Here, x and z would have been the independent variables, and y would have depended on both x and z. And as Ahmad points out, z equals f of xy means that z depends on x and y, where x and y are the independent variables themselves. So by writing this and asking these two questions, it's understood that x and y are independent and z depends on both x and y. But the question could have gone another direction, and so your question makes complete sense, but that's not our assumption. 2z dz dx minus 2, the derivative of this with respect to x, which is dz dx, equals the derivative of 4, which is 0. So Brun asks, how do we know which one we pick as independent variables? Is it mentioned in the question? It has to be understood in the question. And by writing this, that dispels any ambiguity. It's understood, or by writing this, it's understood that z is a function of x and y are the independent variables. Ahmad, there's no need to introduce matrices here, it's immediately clear. You can solve for dz dx. You can probably do that in your head. And you get minus 2x over 2z minus 2, or x over 1 minus z. Yishen, you're introducing new notation. Let's try to stay away from that. Let's not do that. Let's not. Questions here? Well, I mean, we can we repeat? Wait, where did I lose you, Prim? Amar, this is still the partial derivative. The partial derivative of z with respect to x. Z is a function of two variables. It's a partial derivative. Punya, where did I lose you here? I differentiated the whole equation with respect to x. I get this. And now you want to solve for dz dx. So bring this to the other side, factor out a dz dx, and divide. Yeah, we factored and divided. Let's repeat with dz dy. Start with your equation again. Differentiate the whole equation with respect to y. The derivative of x squared, that's 0 because x is treated as a constant. The derivative of y squared, minus 2y. The derivative of z squared, that's something squared, so 2z, times the derivative of the inside. Z is a function of both x and y. Minus 2, the derivative of z with respect to y. The derivative of 4 is 0 again. And it's easy to see by the same process, right? Bring this to the other side, factor out a dz dy and divide. We get y over z minus 1. So since z is a function of x and y, we cannot consider dz dx as a constant, correct? Yeah, well, I mean, so dz dx is not necessarily 0. Yeah. Let's do one more example. You get is that Prudin is asking, is there a way to find dz dx and dz dy without having to do the computation? No. No. I think that's the only way here. The only easy way. All right. Let's work out the partial derivative of f. A link between both what? Both dz dx and dz dy? Perhaps you've noticed that the denominator is the same, essentially. I mean, I changed it in the first one, but it's essentially the same. So maybe that's the link you're referring to. Very nice observation. And there is a relationship. We're going to see that when we define the implicit function theorem in higher dimensions. So we'll probably do that on Monday. We'll see the link then. It's not as easy as you would think. Let's talk about the derivative of f with respect to x here. You know what to do. This is y squared plus 1, or let's say plus y cubed over 2 root x. Why am I back to this simple example? Well, I want to point out that this is now a new function of x and y. So it makes a lot of sense to ask, what about the derivative of this with respect to x and with respect to y? So in other words, what about higher derivatives? Very much like we did in Cal 1, where we differentiated once and then we differentiated again to get the second and third and fourth derivatives and so on. Here we can do the same thing. We can ask, what is the derivative of this with respect to x? What is the derivative of this with respect to y? So if you differentiate the whole thing with respect to x, let me take some time to introduce notation here. The derivative with respect to x of this, well, you've got two d's, so d squared, and you've got two dx's, so dx squared. The derivative of this with respect to x is 0. The derivative of this with respect to x minus y cubed over 4x to the 3 over 2. Similarly, if we had the f dx as y squared plus y cubed over 2 root x, if you differentiate the whole thing with respect to y, if you want to integrate, so Ahmad is asking if we want to integrate a function with dx, dy, dz, do we just integrate 3 times, each time with respect to a different variable? That's exactly what you're going to do. Exactly that. Because when you differentiate with respect to x, y, and z, That's exactly what you do. You differentiate 3 times, each time with respect to a different variable. Let me, right, I mean, in the same way that we introduced notation here, observe, again, 2d's, so d squared, but now it's dy dx. So Ryan is asking, when a question wants us to find partial derivatives, we just differentiate as we're doing right now. Exactly that. So here, if you differentiate with respect to y, 2y. Here, 3y squared over 2 root x. Right? This 2 root x is treated as a constant because it does not depend on y. Thomas is asking, is there a difference between d by dx and df dx? Well, it's the same difference as with d by dx versus df dx. What's the difference with the pair on the bottom? Prin, let's postpone your question until the end of class. We can discuss that together. Well, I mean, with the whole class as well, but the short answer, there is a way. Yes. Would this second derivative be the same if we were to differentiate with respect to y and then with respect to x? It's an excellent question. Yeah, so Blue Pill is suggesting that the difference between these two is the same as the difference between those two. Correct. But my question is, what is the difference between these two things? Anyone? I'm sure this is a question a lot of people had in Cal 1. But we're in Cal 3 now. You should have figured it out or asked somebody. Anybody? Does anybody know the answer to that? One we take F, the others in general. Not really convinced. Well, maybe. Well, exactly. One is a function, one is an operator, right? This is the derivative of f. This is the derivative of f. You have a function f and you've differentiated f. This is the verb, if you will. Here you are differentiating something. Here this is the noun, this is the derivative of f. So this is the operation, the action of differentiating. It's an operator, as Aaron suggests. It operates on functions. This is an operation you are doing, an action you are doing on something. This is once that operation has been done. And Cecile is asking the same question as, who was asking that? As Amar. And it's an excellent question. And let's take this example to illustrate. But yeah, so this is the verb here. to answer that. This is the verb, this is the noun. This is the derivative of f. This is the action of taking the derivative. Let's work out the derivative of f with respect to y, which is 2xy plus 3 root x y squared, easily seen. And now let's ask the question, what is the derivative of this with respect to x? Right, so we're looking at higher derivatives again. Again, let's not talk about total derivatives. I'm not going to talk about it in class. Well, I don't plan to anyways, but if people keep bringing it up, I'm going to have to talk about it at some point. Again, this is d squared f by dy dx is not the total derivative. It's the second derivative with respect to y and x. If we differentiate this new function with respect to x, again, let me introduce notation here. This is 2d's and dx dy. So that's the notation in use. And what do we get here? We're differentiating this with respect to x. We get a 2y plus this 3y squared is fixed. The derivative of square root of x is 1 over 2 root x. Notice that they're the same. Well, this is our first example. Does this always happen? Too soon to tell. Let's finish this example up by looking at the second derivative with respect to y. Right? If you were to differentiate this whole thing with respect to y again, you would get the second derivative with respect to y. What is it? 2x plus 6 root x y. So Yishen is asking, there's nothing like df, dx, dy or something? It had, right. So correct, it has to be d squared. D squared meaning the second derivative. And of course, there's no need to stop at the second derivative, right? You can differentiate this with respect to x and y again and get the third derivative and so on and so on. And it's all good. We've introduced notation, right? If you have dx, df, dx, and you differentiate the whole thing with respect to y, you get d squared f by dy dx. It's understood that you differentiate with respect to x first and then with respect to y, right? But in the fx notation, right, this is the same as that. If you want to illustrate the second derivative, where you differentiate it with respect to x first and then y, x first and then y. So it's actually the opposite. But it makes complete sense, right? Because here, you're differentiating with respect to x first and then y. So it makes sense because it's like an operation here. Whereas here, It's like if you were reading x first and then y, because you read from left to right. Quinn is asking if the first is the same, aren't all of them the same too, with respect to the derivatives? An excellent question and an excellent observation. We'll address that in a moment. But before we do so, let's just do a few examples from the book where we are asked to find all second derivatives. Tony is asking if we can represent the second derivative with respect to x as f of x squared. No. These are the only two notations in use. Either d squared f by dx squared or fxx. Those are the only two equivalent notations for the second derivative with respect to x. Let's find all the second derivatives of this function where a and b are real numbers. df dx. The derivative of this with respect to x, derivative of ln is 1 over times the derivative of the inside, because the derivative of by is going to be 0 with respect to x. So this is just a over ax plus by. df dy, similarly, df dy. You can do that in your head, right? Derivative of ln is 1 over, so 1 over that, times the derivative of the inside with respect to y. This is only x's, that derivative is going to be 0. So you'll get a b on top. Does everybody see that? b over ax plus by. All right. What about the second derivative? So d squared f by dy dx. I don't know what I'm doing there. D squared f by dx squared. Differentiate this with respect to x. I'll give you a minute. I'm sure you can just read it off. Can you? Is that right? What about d squared f by dy dx? Differentiate this with respect to y. Can you do that in your head? Minus ab. What about d squared f by dx dy? What if we differentiated this with respect to x? Does everybody have it? Minus ab over ax plus by all squared. Are all second derivatives mean all four of the second derivatives? Absolutely. Absolutely, we mean all four of these second derivatives. And finally, df, d squared f by dy squared. So the derivative of this with respect to y, which is easily seen to be negative b squared over ax plus by, all squared. And wouldn't you know it, again, these two things are the same. Well, that's just two examples. Avery wants to know why it's negative AB here. Remember that df dy was b over ax plus by. And then we want to differentiate the whole thing with respect to x. Right, with respect to x. So here I'm treating this as b ax plus by to the negative 1. So the derivative is going to be negative b ax plus by to the negative 2 times the derivative of the inside with respect to x. So this is going to be 0, and you just get an a here. So that's why it's negative ab over the denominator squared. All right. Consider this. T is a function of r and theta. Let's differentiate with respect to r, with respect to theta. See what happens. Well, let's use the other notation. TR. So minus 2 e to the minus 2r cos theta. T theta is minus e to the minus 2r sine. And now let's take these second derivatives. T r. The derivative of this with respect to r, that's easily seen to be 4 e to the minus 2r cos. What about T r theta? It's the derivative of this with respect to theta. Derivative of cos is negative sine. So we get this. T theta r is the derivative of this with respect to r. And finally, t theta theta is that. And once again, if Yushen is asking if we can denote TRR as TR squared. Let's not do that. Let's not do that. Because that would confuse people into thinking that maybe you're differentiating with respect to R squared. And it's questionable. Right? Because you might have a variable R squared. And that would open up a whole can of worms. What are we differentiating for T theta R? T theta R here, you differentiate with respect to theta first and then R. So if you differentiate this whole thing with respect to R, that's what that is. It's the derivative of this with respect to R. Theta first and then R. Here it was R first and then theta. Ryan is asking, do we have to write out all 4 types of derivative on an exam? Well, I mean, it depends what the question is asking. And why stop at the second derivative? Why not talk about TRR, R, TRR theta, TR theta R, T theta RR, and I mean, here you have 8 derivatives. So why stop at 4 when you can go to 8? And then why stop at the third derivative when you can go to the fourth derivative, and so on and so on, right? So, yeah. On an exam, you just want to do what the question is asking. Here they were asking for the second derivatives. So there are 4 second derivatives. There it is. So the question will ask you, well, the question will ask you exactly what it wants. There's not going to be any ambiguity. And here, I'm sure all of you have noticed, once again, that TR theta is the same as T theta R. These derivatives have a name. They are known as mixed partial derivatives. Right? Because the subscripts are mixed. Here it's R and R, it's the same. Here it's theta and theta, it's the same. But here they're different. They're mixed, known as mixed partial derivatives. Well, Amar is asking, when they're asking for the second derivative, do we need to show both T theta R and TR theta, even though they're the same? We don't yet know that they're the same. But now the question arises naturally, because we did 3 examples, and they're the same in all 3 examples. Question is, are they always the same? And this is where Kleros Theorem comes to answer that question. Do we have a name for TRR or T theta theta? Well, Brun, very nice. The question is going to naturally ask itself, what about these? Are these the same? Where you've got two r's and one theta, right? If t r theta is the same as t theta r, then these two will have to be the same. And if the derivative with respect to r and theta is the same as theta r, then these two will have to be the same, and consequently they will all have to be the same if, well, let's state Kleros theorem, and we'll see under what conditions that is true. Let f be defined on a disk that contains AB. So here f is actually a function of x and y. I'm defining it in two space for convenience. Be defined on a disk that contains AB, and f of xy and f of yx are both continuous. On AB. No. Was a bit hasty there. Are both continuous on the disk. Then the mixed partial derivatives are equal at AB. So I'm offering this without proof, but Kleros theorem tells us when the mixed partial derivatives are equal. As long as they were continuous on a disk containing the point, then you have equality of the mixed partials. And that extends to, well, first of all, higher dimensions, right? If you had a function of 3 variables, you would want continuity on a ball containing the point. And that also extends to what I just rubbed off here. TR theta theta is going to be the same as T theta R theta, which is going to be the same as T theta theta R, assuming continuity of the mixed partials. Well, Yishen is asking, is it possible that the mixed partials will not be the same? And it is possible. And we'll do an example momentarily if we have time in about half an hour. But before we do that, let's take an example where the question is asking us to verify Kleros theorem. for the function all right. So verify Kleros theorem. In other words, verify that the mixed partial derivatives are the same. What is ux? Derivative of the exponential is the exponential times the derivative of the inside with respect to x, you get a y. Sine y is fixed as it does not depend on x. And then if you differentiate this with respect to y, well, now you've got a product, this times that. So product rule kicks in, derivative of the exponential is the exponential times the derivative of the inside with respect to y this time, you get an x. Leaving y sine y fixed, and then leave the exponential fixed, and differentiate this. But this is again a product, so product rule applies. We're differentiating with respect to y, so that is sine y plus y cos y. And now if you differentiated this with respect to y first, it's a product. So product rule applies. Derivative of the exponential is this times the derivative of the inside, you get an x. Leaving sine y fixed, plus leave the exponential fixed, differentiate the sine, and you get a cos. Finally, uyx, differentiate this with respect to x. So here you've got a product. So product rule applies. Derivative of the exponential is the exponential times the derivative of the inside. Derivative with respect to x of the inside, we get a y. Leaving x sine y fixed, plus leave the exponential fixed, differentiate x sine y with respect to x. Derivative of x is 1, leaving the sine y there. And then derivative of the exponential again, e to the xy times the derivative of the inside with respect to x, that's y cos y. Are they the same? E to the xy, y cos y, e to the xy, y cos y, these are the same. E to the xy sine y, e to the xy sine y, these are the same. And x sine y, y, e to the xy, these are the same. It's clear that u of xy is the same as u of yx. So this theorem is an if and only if. It is not. It is not an if and only if statement. This is a sufficient condition for equality of the mixed partials. What do we ask for here? F of yxy. Question is asking for f of yxy. You know what that means. That means the derivative of y first, and then x, and then y again. By Kleros theorem, if everything is continuous, then this should be equal to f of xyy and should be equal to f of yyx. I'm going to let you work that out. I'm going to let you convince yourselves of that. But let's just find this one. The partial of f with respect to y, we have sine of something, the derivative is cos, times the derivative of the inside with respect to y, so we get a times of 5. And then if you differentiate that with respect to x, the derivative of cos is negative sine times the derivative of the inside with respect to x, which is a 2. We still have that 5 outside. And if you differentiate with respect to y again, the derivative of sine is cos, so negative cos, times the derivative of the inside with respect to y times a 5, and you still have that 2 and that 5 outside. There it is. So this is negative 50 cos 2x plus 5y. Correct. Even if the mixed partials are equal, it does not imply that they were continuous to begin with. How are we doing here with Kleros theorem and higher order partial derivatives? I mean, look, I think it's pretty clear here, right? 2x plus 5y is a polynomial in x and y, so that's going to be continuous. The derivatives of sine and cos, well, derivative of cos is sine and derivative of sine is cos. Anyways, I mean, it's, you know, these polynomials are, sorry, did I say polynomials? I meant, you know, these trig functions are continuous everywhere. So these are just the composition of either sine or cos with a polynomial, so you know it's going to be continuous. You know the partial derivatives are always continuous, and you can make that argument. So, I mean, you know, if the question was asking for you to work out all the mixed third order partial derivatives, and you want it to be efficient, then you could make the argument that you don't need to calculate these. You just need to calculate that one, and they're all the same because it's either going to be sine or cos times a number composed with a polynomial, so you know it's going to be continuous. And that would be a very nice argument to make on an exam. Questions? Anyone? Let's consider a nice exercise here, which really should have been consider this nice exercise, which should have been one of the midterm questions. Ahmad is asking, should we check continuity first before taking the mixed partial derivatives? Usually you don't need to worry too much about that. Usually. But here you better worry. Here you really need to worry. And what we have here about 101, I'm not sure what you mean by 101. Oh, yeah, well, right. Yeah, this question, right. Well, I mean, I understand what you're thinking. I know what you're thinking. Because in Calculus 1, we had this nice result that if a function is differentiable, it had to be continuous to begin with. This is not true of partial derivatives. Because think of what happened. Think of how we introduced the partial derivative. I said, or I suggested we had this function hovering above. And if you fixed a point AB and looked at its image, we were cutting this graph parallel to the x-axis and looking at the curve and figuring out the slope of the tangent line on that curve. And same in the y direction. So observe that in between here, there could be chaos. And we wouldn't even know. Because all we're looking at is on this cut and on that cut. So we're not, by looking at the limit, we're not considering all the other paths. We're not even, they don't even exist as far as we're concerned, and we don't care. We just are restricting our attention to these two curves. So while in Cal 1, if a function was differentiable, it had to be continuous. That result does not extend to partial derivatives. A function may have a partial derivative even if it's not continuous. So here, to answer Brun's question, we don't care about continuity. The question is not asking us to determine if this function was continuous to begin with. All it's asking are for the mixed partial derivatives at the origin. But let's talk about. Let's talk about something. What do we want to talk about? Let's talk about the fact that if you're away from the origin, if you're anywhere other than at the origin, this is a polynomial divided by another, and this denominator is never zero, except for the origin. So anywhere else, the function is very well behaved. It's continuous, because it's one polynomial divided by another. You can take the derivative with respect to x and with respect to y everywhere other than the origin without worrying too much, just by applying the quotient rule. And that's very nice. In fact, why don't we work that out? If you're not at the origin, what is the derivative with respect to x? Let's work that out. What is the derivative with respect to x if you're not at the origin? Well, it's just the derivative of this. So this is a quotient. Quotient rule applies. V u prime, the derivative of this with respect to x, that is 3x squared y minus y cubed minus u v prime, the derivative of this with respect to x, which is 2x, all over v squared. Can we simplify that? Does anything cancel? Let's try to expand, see what happens. This is 3x to the 4 y minus x squared y cubed plus 3x squared y cubed minus y to the 5 minus 2x to the 4y plus 2x squared y cubed. Anything? Well, these two cancel out. Let me rewrite it here. So this and this, we get an x to the 4y. The x squared y cubed. So plus x squared y cubed. No, we have another x squared y cubed here. So that's going to be a plus 4. Minus y to the 5 over x squared plus y squared, all squared. So to answer Rand's question, if the question is asking for you to determine continuity, how do you do it? You use the limit and methods we learned yesterday. Absolutely. Exactly that. So that is the partial derivative of f with respect to x for any point other than 0. Very well. What about the derivative of f with respect to x at 0? Well, this is a piecewise defined function. So you know what to do. The only way you can find the partial derivative with respect to x is by using the definition. You have to use the limit definition here. So the derivative of f with respect to x at the origin is the limit as h goes to 0 of f of 0 plus h 0 minus f of 0, 0 over h. What is that? Well, this is f of h0. So everywhere you see a y, right? First of all, we're taking a limit as h goes to 0. So you know that you never actually reach 0, but we want the behavior as you're getting closer and closer to 0. So this point, h0, is never the origin. So you are allowed, well, not only are you allowed, but you have to use this. And when x is h and y is 0, we get h cubed times 0 minus h times 0 cubed over 0 squared, no, sorry, h squared plus 0 squared. So that is your function at h0. F of 0, 0 is 0. But this thing is 0. So this whole limit is 0. The partial derivative of f with respect to x at the origin is 0. So let's put all of that together. We found the partial derivative of f with respect to x to be this at points other than 0. And it's 0 at the origin. We never talked about continuity at 0. Yishan is asking why we have to go back to the limit definition to find the derivative at 0. We never talked about continuity at 0. It's because the function is a piecewise defined function. So you, very much like in Cal 1, where you had to use the limit definition when you had such a piecewise defined function, you have to do the same thing here. How are we using the function when it isn't defined at 0, 0? I'm not sure what you mean. It is defined at 0, 0. The function is equal to 0 at 0, 0. How are we doing? Everybody with us? So we have just worked out the partial derivative of f with respect to x at all points. It's 0 at the origin, and everywhere else, it's this. But we're not, so Amar is asking why we're using this in the limit definition when it doesn't apply at the origin, but we're not using this at the origin. At the origin, we're using 0. We're using this at the point h, 0. And h is never 0. Right? So h is never 0, so the point h0 is not the origin. So we have to use this one. Turns out that the function is 0 regardless there. But that's the one we had to use. Now that we have f of x, well, the partial derivative of f with respect to x, let's work out f of xy at the origin. And again, partial derivative of f with respect to x is a piecewise defined function. So we again have to resort to the limit definition. This is the limit as k goes to 0 of f of x 0, 0 plus k, minus f of x 0, 0 over k. Partial derivative of f with respect to x at the point 0k, where k is not 0, right? We're looking for the... Jordan, this is calculus 3. Where k is not 0, right? We're looking for the limit as k goes to 0 but never reaches it. So the point 0k is not the origin. So we're plugging it into this, and when x is 0 and y is k, what do we get? X is 0, that's gone, y is k, so we get a negative k to the 5. X is 0, y is k, so we get over k to the 4. Fx at the origin is 0, all over k, and you see that this limit is easily seen to be negative 1, thank you, negative 1. Now repeat. Find the derivative of f with respect to y everywhere. Let's cheat. We're going to cheat. Let me give you a moment to prepare yourselves by observing or by making this beautiful observation. Look at your function. What happens if you interchange x and y? Well, Tony is asking, can we prove continuity to make sure fxy is equal to fyx? In fact, fxy will not be equal to fyx here. That's the whole point of this exercise. The mixed partial derivatives are not equal here. Why didn't we find f of xy at all points? My point was to show you that f of xy at 0, 0 is not equal to f of yx at 0, 0. So the mixed partial derivatives are not equal at the origin. That was the whole point of the exercise here. Notice that if you interchange x and y, denominator stays the same. Here, this becomes y cubed x minus yx cubed, which is really the negative of this function. So the derivative with respect to y is going to be negative of this derivative with the x's interchanged with y's. Well, you can do that. That's fine. But my point was that in this particular example, f of xy is not going to be equal to f of yx. That was the only, at the origin. That was my only concern with this example. You can do whatever you want. You can do as much work as you want, but all I wanted, the only reason I presented this example was to show you an example where the mixed partial derivatives were not equal. They will be equal everywhere else, though, but not at the origin. So by this observation that if you interchange x and y, you get negative, the derivative with respect to y is going to be negative of this with the x's and y's interchanged. So it's going to be negative y to the 4x plus 4y squared x cubed minus x to the 5 over y squared plus x squared. You don't have to take my word for it. You can do it the long way and convince yourselves that that's what you get. And if you work out the partial derivative of f with respect to y at the origin, let's do that. The partial derivative of y at the origin, this is f of 0, 0 plus k, minus f of 0, 0, over k. If x is 0 and y is k, that's 0, so it's again 0 over k squared minus 0 over k, which is 0. So the derivative at the origin is 0. And then if you find f of yx, which is the limit as h goes to 0 of fy 0 plus h 0 minus fy of 0, 0. If x is h and y is 0, so that's gone, x is h, so you get h to the 5. Y is 0, x is h, so over h to the 4. Partial derivative of f with respect to y at the origin is 0 over h. This is easily seen to be 1. And there you have it. The simplest example where the mixed partial derivatives are not 0. F of yx at the origin is 1, and f of xy at the origin was -1. They are not equal. How are we doing? Questions, anybody? Questions on this? How are we doing that? So let's say, well, yeah. Yeah, no. Absolutely. Because it's a piecewise defined function, we have to use the limit definition. Well, I'm suggesting that if you interchange x and y, you get negative of the function. So the derivative is going to behave in the same way. You don't have to take my word for it. Please do it the long way. See what happens. Ahmad is asking how many questions are going to be on the midterm. Well, here's my question to you. Do you want partial differentiation on the midterm? Because right now, if we don't include partial differentiation, it's really just sequences and series. I mean, I don't know that I want to put an epsilon delta question. So continuity is going to be out. Right now it's 3-to-1. Wait, yeah, 3-to-1 for partial differentiation. 4-to-1. The vote is still open for another minute. Everybody wants partial differentiation, then we'll put some partial differentiation on it. Very good. Very good. All right. Yeah, Yushen is asking, how can we predict? I mean, you can't. You can't. I mean, I was not going to ask an epsilon delta question anyways, so let's not worry about that. Nima, what is your question, or is it like 140? Was there a first? Oh, will epsilon delta appear? There will be no epsilon delta definition. No epsilon delta proofs on the midterm, nor on the final. Evan is asking, find the exact error in using a Taylor polynomial. You just write f of x minus t of x. That's it. They want the actual error, not an approximation on the error, but the actual error. How many questions are going to be on the midterm? It's probably going to be a short midterm because frankly, I don't even have any good questions. I have one good question. So let's say right now I'm thinking maybe 4 or 5 questions on the midterm. Let's call it 5 to be safe in case some genius questions arise from now until tomorrow. Right, Thomas was asking about the nth derivative. I think somebody had asked for that as well. Pun, yeah, exactly. Pun's question is exactly that. Let's discuss that. It's a beautiful observation. It's a beautiful observation that in a Maclaurin series, right? Well, I mean, how do Maclaurin series come about? Right? Remember the long way, we have a function and its value at 0, and then the derivative at 0, and so on. So if you have all the derivatives of a function at 0, then you essentially have the function itself via the Maclaurin series. And vice versa. All the derivatives of the function are incorporated in the Maclaurin series. So here's a nice question. Suppose I give you a function like this, and I ask you, what is the 101 derivative of that function at 0? When Kian is asking, is it 5 big questions with multiple parts? I mean, it's going to be 5 big questions, yes. I don't know about the multiple parts, but you should expect them to be, I mean, I'm not going to ask you to find the partial derivative of f with respect to x for f being x squared y cubed. Right? So it's not going to be questions like that. Again, it's going to be questions where you might not be able to use Wolfram alpha immediately. And again, right, Wolfram alpha is there, but really you should be doing the work and then using Wolfram alpha to check your answer. So, right, I mean, here's the question. What if I was asking you for the 101st derivative at 0? Well, I mean, of course, you have options. And one option is to differentiate this 101 times. We're not going to do that. Instead, we're going to be smart and remember that if you have a Maclaurin series, for a function, Maclaurin series is this. And you see that all the derivatives of the function at 0 are somehow incorporated into the Maclaurin series. In particular, this is some stuff plus when n is 101, you have the 101 derivative at 0 over 101 factorial x to the 101. And then other stuff. And what I mean by other stuff is, here I mean powers of x that are less than 101, and here powers of x that are greater than 101. So you see the 101st derivative is incorporated into the coefficient of x to the 101. So now we have to ask ourselves, well, what is the coefficient of x to the 101 here? Well, you know that cosine has Maclaurin series, negative 1 to the n, x to the 2n over 2n factorial. So if you multiply by x cubed, you get this. And now all we need to figure out is what is the coefficient of x to the 101. Well, if n is 50, you have an x to the 103, so that's too large. If x is 49, 49 times 2 is 98, 99, 100, 101. So this is stuff plus, when n is 49, you get negative 1 to the 49, x to the 101 over 98 factorial. And now compare this theoretical coefficient of x to the 101 with the actual coefficient of x to the 101. So the 101th derivative at 0 over 101 factorial, which is the coefficient of x squared, of x to the 101, should be equal to negative 1 to the 49 over 98 factorial. So 101st derivative is going to be 101 factorial over 98 factorial, and negative 1 to the 49 is negative 1. So this is 99, 100, 101. There it is. So Ren is asking, for piecewise function, why did you use the limit method to evaluate the second derivative instead of taking the derivative directly? If you take the derivative directly, it's going to be the derivative at all points except at the origin. And the origin is what I was interested in. Brune is saying we find the Maclaurin series representation and solve for the original version. Yeah, exactly that. Yeah, exactly what we did. Ran also for a piecewise function, we check when you're at the origin. Yeah, exactly. I mean, the function is piecewise defined. So at the break, which was at the origin here, you have to use the limit definition. Exactly what we were doing in Cal 1 anyways. Bryn is asking, does this work with multivariable? You mean multivariable Taylor series? We will get to that, absolutely. What if you do not have a series of the form Cn x to the n? For example, cos x minus 1 over x cubed. I mean, you can do it. Do it. We did an example like that in class already, where we were finding the limit as x goes to 0 of cosine x minus 1 over x cubed. And we did that by finding the Taylor series or the Maclaurin series for cosine x, subtracted 1, factored out an x cubed, everything works very nicely. Amar is asking for the series k ln k over 1 plus k cubed. Does this series converge? That series does converge. You can do a comparison test and show that this is less than k to the 3 over 2 over 1 plus k cubed. And then do a limit comparison here with the series 1 over k to the 3 over 2. This one converges, so that one converges, and since the bigger one converges, the smaller one converges. You need to prove that k ln k is less than or equal to k to the 3 over 2. I'm leaving that to you. Ahmad is asking if I'm planning on teaching an ODE course in 2021. I am not. I already have the teaching assignment. It's 262 again. So no. But look, I mean, there are excellent teachers, and it's good for you to get a break from me and see what other people have to say. Yining is asking, can we only approximate a limit to a specific decimal place for an alternating series? As opposed to what? Finding the actual sum that the series converges to? In some cases, you can find the sum. Anna Maria is suggesting that the nth derivative of that function is no longer the coefficient. Correct. It's not, but it is related to the coefficient, right, in this respect. Avery would like to do another example when we have a large decimal and we make it into a fraction. Let's do it. The 3 to 6 is repeating. Still not sure what you mean, Anna Maria. You could find the Maclaurin series for this function. You can find the Maclaurin series for this function. And then you could ask for the 100th derivative. Evaluate it as 0. Still in exactly the same way. In exactly the same way we did it. Don't worry about the -1. Find the Maclaurin series for this. You subtract 1 from it. You divide by x cubed. And then you look for the coefficient of x to the 100. Or x to the 101 or whatever. Whatever. So here the 326 is repeating, so this is going to be 417 plus 326 over 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. Plus 326 over 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And so on and so on. Or 417 over 100 plus take out a 1 over 100, or take out a 326 over 100, and you get 1 over, so you're taking out 2 zeros, you're going to have 1,000. And then 326 over 100, you get 6 zeros. Or if you prefer, if you factor out a 326 over 100, you get 1 over 1,000. And this is 1 over 1,000 squared. And then the next one would be 1 over 1,000 cubed. You can write down a few just to convince yourselves, but it's important to understand what's happening. And then you recognize that as a convergent geometric series. And this converges to the first term over 1 minus 1 over 1,000. So that is 417 times 999 plus 326 over 999,000. No, 2 zeros. All right, let's do Yining's example, and then that'll be it for the day. Approximate cosine 1 to 3 decimal places. So first of all, you would start by finding the Maclaurin series for cosine x. But I mean, we've done it already. I'm sure you've done it many times, and you know very well that that's what it is. And this converges for all real numbers. You know the interval of convergence is all real numbers. All right, so in particular, cosine 1 is therefore negative 1 to the n over 2n factorial. That's what cosine 1 actually is. This series converges to cosine 1. But what is that? And we still don't know. What we can do is we can add a few terms to give us an approximation. And then we're left with the rest. So if you bring this to the other side, the difference between cosine 1 and your approximation is this rest. So the difference between this is that, and this is an alternating series. First of all, you should check that it satisfies the alternating series test hypotheses. So that's important to do on an exam or something. Make sure that this satisfies the alternating series test hypotheses, but it does. And consequently, this is less than or equal to the next term in line, which is 1 over 2k plus 1 factorial. So that's 1 over 2k plus 2 factorial. And we're going to make sure that this is less. We want 3 decimal places. So 1, 2, 3, and 5. Just as a starting point, you know that we're just using this as a starting point. This may or may not be sufficient. We might have to adjust, but let's not worry about it for now. Well, first of all, question 1 on the 141 final was not about curve fitting at all. You didn't have to figure out what functions satisfied that. All you had to do was do the integration. What are you asking? If f and g are equal, what is this r squared equals 1? Do you mean a circle of radius 1? Are you saying that if f and g are equal on a circle of radius 1, then they have to be equal everywhere? Okay, fine. That's fine. I mean, it was, so you're asking, is there only one function that fits all points? The answer is no. There are infinitely many functions that fit all of these points, but it doesn't matter. It doesn't matter if you found one, and that certainly was not the intention of the question here. And if you wasted hours doing that, I mean, it's well, like you said, it's a waste of time. Because, I mean, it's number one, it was the easiest question in the whole exam, pretty much. It was a confidence builder, really. So, you know, by trial and error here, if k is what? Well, first of all, what is that? 10, 100,000, 10,000, that is 1 over 2,000. So if k is 5, you have 1 over 12 factorial. I'll be lazy, and Wolfram Alpha is going to tell us what that is. That is way too big. Jesus, yeah, what was I thinking? Way too big, way too big. It's only 1 over 2,000. Take k to be 3, perhaps. That's 1 over 8 factorial. Even that is pretty big. K is 2, 2, 4, 6, 1 over 6. Yeah, that might not do it. So if k is 3, 1 over 8 factorial. That is 1 over 40,000. 320. So that is less than 1 over 2,000. And if k is 2, you get 246, 1 over 6 factorial, which is 1 over, I believe, 720. Doing this from memory here. No. 1 over 720. There it is. And that is not less than 1 over 2,000. So this is, so k equals 3 is the important thing. And when you sum from 0 to 3 of -1 to the n over 2n factorial, again, Wolfram alpha will tell us what that is. Point 0.54, 0.5402, where the 7 repeats. Very good. And you see the issue, right? If we stuck with our 0.0005, if the error was within this, then if you subtracted this 4, I mean this 0, in fact this 40 would become a 39, right? If you subtracted this error, you'd get 0.5397. So it would not only affect the third decimal place, but also perhaps the second. Luckily for us though, by using k equals 3, we actually have 1 over 40,000. And what is that? 40,320. That is actually 4 zeros followed by a 2. So 1, 2, 3, 4 zeros followed by a 2. Oh, that's not an issue. So 1, 2, 3, 4 zeros followed by a 2 and a 4 and something something. So whether you're adding or subtracting, it's going to affect at most the fourth digit. The first 3 digits, right? So whether it's plus or minus, the first 3 digits are always going to be 540. And so with confidence now, you know that the first 3 digits are 540. So we plugged in x equal to 1 into our series because we were looking for cosine of 1. Absolutely. Is it possible to find fx? Well, the point is, Ahmad, there are infinitely many such functions. But all you needed was the information that was given. You didn't need to find a function. Yeah. So, I mean, it's probably doable to find a function, and in that way you could end up with the right answer. Not what we had in mind, but yeah. All right. Thank you all for coming. If you've got questions, I will just send me an email. And otherwise, Friday, 2 p.m., the the midterm will open up on CrowdMark. You'll get an email from CrowdMark as well. Thank you very much for coming. I'll see you next time.